This is a video walkthrough for Practice 9C. In number 1, we're asked what the purpose of a logarithm is. And the purpose of a logarithm is to solve an equation for the exponent. An example, 2 to the 3 equals 8 is solved for the 8. The 8 is by itself on one side of the equation in terms of the 2 and the 3. This is also equivalent to writing 2 is equal to the cube root of 8. Now 2 is expressed in terms of the 3 and the 8. But there is now a third way to express this relationship, and that is to solve for that exponent 3. 3 is equal to log base 2 of 8. All right, in number 2 and 3, we're asked to write the equation in exponential form. So when you're writing a logarithmic equation in exponential form, you have to ask yourself a question first of all. What is the base? When you say this logarithm, you say it log base 2 of 32 equals 5. So we know that the base is 2. Next, what is the exponent to which that base is raised? And a logarithm equals an exponent. This logarithm is equal to 5, so that means that the exponent is equal to 5. And then 2 to the 5th power is equal to, and you put the 32 on the other side of the equation. And in number 3, similarly, what's the base? The base is 3. What's the exponent? A logarithm equals the exponent, so the exponent is -4. And then that leaves us 1/81st for that exponential expression to be equal to. Similarly, in number 4 and 5, we're going to take an exponential equation and write it in logarithmic form. So the very first thing that we're going to do is write LOG. And after LOG, we say LOG base what? Log base what? And the base of this exponential expression is 9. So 9 goes as a subscript below the line on which you wrote log. And then the logarithm is equal to the exponent, so we know that it's equal to 3/2 on the other side, so it must be the log base 9 of 27 equals the exponent 3/2. In number 5, log, and the base is 5, so log base 5 of 1/25 equals the exponent -2. All right, in 6 through 23, we're evaluating each logarithm. Remember that a logarithm is equal to an exponent, so we have to be thinking the base is 5, the exponent is what I don't know, and that equals 125. And of course, 125 can be re-expressed as 5 cubed, so this logarithm is equal to 3. All right, for 7, log base 3 of 81. So my thought process has to be base 3 raised to what exponent, the exponent that I don't know, equals 81. And of course, 81 can be re-expressed as 3 to the 4th power, so this logarithm is equal to the exponent 4. In number 8, we have a common log. A log written LOG without a base specified. In this case, we assume the base is 10. So base 10 raised to the exponent that I don't know because we're trying to find the value of the log is equal to 10,000. And 10,000 is 10 raised to the 4th power, so this logarithm is equal to 4. In number 9, we're looking for the log base 6 of 6, so my thought process is base 6 raised to the unknown exponent equals 6, and that should be 1, so log base 6 of 6 is 1. In number 10, my thought process is I'm looking for the exponent that I need to raise 3 to in order to get a result of 1. And of course that would be the 0 exponent, so log base 3 of 1 is equal to 0. In number 11, I need to be thinking base 3 raised to the unknown exponent is equal to 1/27th, and 1/27th is 1 over 3 cubed, which is 3 to the -3. So the value of this logarithm is -3. In number 12, we have a logarithm with an unspecified base, so we'll assume that the base is 10, and 10 raised to the unknown exponent is equal to 1/100th. And of course, 1/100th is 1 over 10 squared, and that's the same as 10 to the -2. So this logarithm has a value of -2. In number 13, log base 49 of 7. Our base is 49. The exponent is unknown because exponent is the value of the logarithm, and that equals 7. So let's re-express using the same base, and then we'll have 7 to the 2x is equal to 7 to the 1, and if 2x is equal to 1, then the exponent is 1/2. So the value of this logarithm is 1/2. In 14, log base 8 of 2. So my thought process is 8 raised to the unknown power is equal to 2. 8 is 2 cubed, and 2 is 2 to the 1. So now we're going to have 2 to the 3x is equal to 2 to the 1. 3x is equal to 1, which makes x equal to 1/3. For number 15, we have a base 8 raised to an unknown exponent equals 4. Both 8 and 4 can be re-expressed in base 2, 2 cubed, and 2 squared. So now we have 2 to the 3x is equal to 2 to the 2. So 3x is equal to 2, and x is 2/3. In 16, log base 2 of 1/16. So my thought process needs to be base 2 raised to the unknown exponent is equal to 1/16. And 1/16 is the same as 1 over 2 to the 4th. 2 to the 4th is 1 over 2 to the 4th is 2 to the -4, so the value of this log is -4. In number 17, this is a base 10 log because the base is unspecified, so 10 raised to the x power is the 5th root of 100. And 100 can be re-expressed as 10 squared, and the 5th root of 10 squared is the same thing as 10 raised to the 2/5 power expressed as a fractional exponent, so the value of this logarithm is equal to 2/5. For number 18, log base 1/2 of 8. I need to be thinking my base is 1/2, the exponent is unknown, and the result is 8. So 1/2 is 2 to the -1 power, and 8 is 2 to the 3rd power. So 2 to the -x is equal to 2 to the 3rd power, so that means that x is going to be -3, and the value of this logarithm is -3. In number 19, we need to be thinking base 27 raised to the unknown power is equal to the square root of 3. So 27 is 3 cubed, and the square root of 3 can be expressed as 3 to the 1/2. So if we equate our exponents, 3x is equal to 1/2, and dividing by 3, x is equal to 1/6. So the value of this logarithm is 1/6. All right, in 20, we have a base 7 raised to an unknown exponent equals the cube root of 49. So 7 raised to the x is equal to the cube root of 7 squared, and the cube root of 7 squared can be re-expressed as 7 raised to the 2/3 power. So the value of this logarithm is 2/3. In 21, we have the log base 6 of 6 times the square root of 6. We can think of this as base 6 raised to the x power is equal to 6 times the square root of 6. Now, 6 is really 6 to the 1 power, and 6 to the 1/2 is the same as the square root of 6. When we multiply like bases together, we add the exponents, so this would be 6 to the 1/2. However, we're going to give our answer in improper fraction form. That is the preferred way to give that. That'll be 3/2. In 22, the thought process is base 4 raised to an unknown exponent is equal to the square root of 2. Base 4 can be re-expressed as 2 squared, and the square root of 2 is 2 to the 1/2. So now if we equate the exponents, we're going to have 2x is equal to 1/2, and if we divide both sides by 2, we're going to get 1/4. In number 23, our base is 1/3 raised to an unknown exponent equals 81. 1/3 is the same as 3 to the -1, and 81 is the same as 3 to the 4th power. So if we equate our exponents, -x is equal to 4, and that means the value of this logarithm is -4. In 24 through 29, we're asked to solve each equation for x, which is now not the exponent in many cases. So the thing that we're going to need to keep in mind when we get to number 29 is we're going to use that hint and try a use substitution. So in 24, if I have the log base 7 of x is equal to 2, it will be helpful for us to put this in exponential form. So our base is 7, the logarithm equals the exponent, so the exponent is equal to 2, and that equals x. So we've already solved for x and just simplify that. X is equal to 49. And in number 25, our base is 4, the exponent is negative 3/2, and that must equal x. And so 4 raised to the negative 3/2 is the same thing as the second root, or the square root of 4, raised to the negative 3 power. So now we just have to simplify. The square root of 4 is 2, and 2 raised to the negative 3 power is 1/8. So x is 1/8. For 26, our base is 1/9. The exponent is what the logarithm equals, and that must be equal to x. So now we have 1/9 raised to the negative 1/2. That's the same as the reciprocal raised to the positive 1/2. And so that's 9 to the 1/2, which is 3. So x equals 3. In number 27, we have our base x raised to the 3/2 power is equal to 27. And so if we can solve a fractional exponent equation by raising to a reciprocal power. So I'm going to raise both sides to the 2/3 power, because when we raise a power to a power, we multiply exponents, and 3/2 times 2/3 is equal to 1. So now we have x to the 1, which is x. And on the right side, 27 to the 2/3 power is the cube root of 27 raised to the second power. We can do those in either order. It's easier to take the cube root first. The cube root of 27 is 3, raised to the second power is 9, so x equals 9. Number 28, our base is x, our exponent is equal to 1, and the result must be 7, so x is equal to 7. Number 29, let's let u equal the inside function log base 3 of x. That will, when we make that substitution, make this equation much easier to solve. So we just replace the inside function with u and then solve for u. So my base is 5 and my exponent is 0, and that must equal u. So it looks like u is 1, and let's remember what u was. U is the log base 3 of x, so now the log base 3 of x is equal to 1. Let's put that in exponential form. The base is 3, the exponent is 1, and that equals x. So that means that x must be 3. In 30 through 35, we're going to evaluate some expressions that are a little bit more complicated than just a simple logarithmic expression. In number 30, we can evaluate the log base 3 of 16 first. The log base 4 of 16 is the exponent to which 4 can be raised to produce 16. So that is 2, and 4 squared is equal to 16. However, there is an inverse property that we can use to get to that result faster. 4 to the log base 4 of 16, if the bases match, base of the exponential, base of the logarithm, then they just undo one another and we get a result of 16. In number 31, we have log base 6 of 6 to the 5th. So we need to be thinking base 6 raised to the x power is equal to that 6 to the 5th power. So x is 5. So this result is 5. Now that is also another inverse property, log base 6 of 6 to the 5. If the base of the logarithm and the base of the inside exponential match, then the result is just the exponent. In number 32, we can't evaluate log base 5 of 29 without a calculator, but we can notice that the bases of the logarithm inside the exponential expression and the base of the exponential expression match, so they just undo one another, and that result is 29. In number 33, log base 13 of 13 to the negative 41 is the exponent negative 41. In 34, we have an inside function, so we're going to work on this one first. So just order of operations, perform the operations inside the parentheses. So my thought process here has to be base 3 raised to what power gives me 3, and that's a result of 1. So that means that this inside parentheses can just be replaced with 1. So now we're finding the log base 7 of 1. My thought process for that one is going to be base 7 raised to the what power gives me 1. And that would be to the 0 power. So 0 is our final result for this expression. We can work 35 similarly. We just want to work that inside parentheses first. So my thought process for this is base 2 raised to the I don't know what the exponent is equal to 8. That means this log has a value of 3. So we can replace the parentheses with 3. And now we have the log base 9 of 3. So my thought process to evaluate that one is base 9 raised to what exponent gives me 3. And if you don't know that one immediately, you can always use common base here. Both of them can be expressed in base 3. If we do that, we're going to get 2x is equal to 1, and x is 1/2. Number 36 through 39, to create a table of values for a logarithmic function, you really just need to keep in mind some things. Let's go ahead and write our x value over here on the left, and the y value is just the log base 3 of that. Now, if you remember that a logarithm equals an exponent, and our exponents can be both negative and positive, I'm just going to replace the exponents with negative 1, negative 2, negative 1, 0, 1, and 2. And if our base is 3, then 3 to the negative 2 is 1/9, 3 to the negative 1 is 1/3, 3 to the 0 is 1, 3 to the 1 is 3, 3 to the 2 is 9. I don't think our last point's going to fit, so we're just going to graph the ones that we have. So x is equal to 1/9, comma, negative y is equal to negative 2, x is 1/3, y is negative 1, x is 1, y is 0, and x is 3, y is 1. That's going to be a graph with a vertical asymptote at the y-axis. All right, in number 37, we can work this one similarly. So x and log base 1/3 of x would give us our y values. And if the logarithm equals an exponent, then the logarithms are just the exponents. So I'm going to put my standard 5 in there for the values of the exponents. Our base is 1/3. 1/3 to the negative 2 is positive 9. 1/3 to the negative 1 is 3. 1/3 to 0 is 1. 1/3 to the 1 is 1/3. 1/3 squared is 1/9. Our first point in this table will not fit. That's okay. We've still got 4 more. So 3 comma negative 1, 1 comma 0, 1/3 comma 1, and 1/9 comma 2. This is going to have a vertical asymptote of the y-axis as well, but the graph is approaching on the top side. In 38, we have a couple operations here. So we have x, and due to the parentheses here, we have to evaluate parentheses first. So x plus 3 is our first operation. Add 3 to whatever the x value is. And then finally, to get the y value, take the log base 2 of that. So since the logs are our exponents, they are negative 2, negative 1, 0, 1, and 2. And our base is 2. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. To get from x plus 3 to x, we have to subtract 3. 1/4 minus 3 is negative 2 3/4. 1/2 minus 3 is negative 2 1/2. 1 minus 3 is negative 2. 2 minus 3 is negative 1. 4 minus 3 is 1. So I'm going to graph our points. I'm going to go left 2 3/4 and down 2. Left 2 1/2 and down 1. Left 2 and down 0. Left 1 and up 1. And right 1 and up 2. And we could actually probably fit in another point here. So let's put an exponent of 3 here. If our base is 2, 2 to the 3 power is 8. And subtracting 3, that gives us 5. So we have a point 5 comma 3 that we could also put on that graph that will give us a much more accurate curve if we put more points in there. So we have that vertical asymptote. This time our vertical asymptote is not on one of the coordinate axes. It is on x equals negative 3. Number 39, we have a very similar looking equation to 38, but the order of operations is different. So when we put in our x values, there are no parentheses, so that means that the logarithm takes precedence first, and then that's going to be followed by the subtraction. So logarithms are the exponents, -2, -1, 0, 1, 2, and our base is 2, so x is 1/4, 1/2, 1, 2, and 4. And to get that last column, we're going to take the logs and subtract 3. So that'll give us -5, -4, -3, -2, and -1. So to graph the points, I'm going to go over 1/4 and down 5, over 1/2 and down 4, over 1 and down 3, over 2 and down 2, and over 4 and down 1. You're going to see sort of the parent function there, but it's been moved down 3. And this time our y-axis is functioning as the vertical asymptote to this graph.